Hello everyone, welcome to this ninth session for the solar training. This session will be presented by Lionel and Philippe, and the title of this session is High PV Penetration in Urban Area, and this is a particular session to present you a research project named eShape. Lionel?
Okay, thank you, Mathilde. So again, good morning, good afternoon, and good evening to all of you, depending where you are located, and welcome to this session. So I would like also to congratulate all of you because, well, basically you almost made it as this session, and the debris session on Thursday is the before last one of this ninth edition of the solar training. So congratulations, it was a long month, fully packed with a lot of information. I'm glad many of you are currently attending. So with the support of my colleague Romain Bessot, Philippe Blanc, Benoît Chouin, Raphaël Jolivet, and I myself, we're going to present you this ongoing works, ongoing development, which is done under a research project called eShape to support the high PV penetration in urban area. So as global words, I would say that this session is perfectly illustrating the relationship between MINES ParisTech and the SoDa Team of Transvalor, and trying to emphasize the articulation of the work which is needed to support the research transfer from a prototype, this is what we are going to present you, or what we call a POC, a proof of concept, towards the product which could be available on the shelf to the end user in the on the SoDa website. So as a key message in this session, you will learn how to invoke, compute, process data and services in order to assess PV variability at urban scale. Throughout this example and this pilot, we're going to walk you through an example of self-consumption for rooftop PV system, and we are going to take the example of the city of Nantes, which is located in France. So here's the outline of this session. So I will introduce the support project, the support research project called eShape, which is a project funded under the European Commission Horizon 2020 framework program. So it will be really fast, but I would like you to have the global support of the development we are currently doing in this pilot. Then I will present you one slide of what is the global architecture which supports the development of this pilot. The idea is for you to basically make sure you understand where are the components located in this puzzle that we are going to develop further on. Then I will leave the floor to my colleague Philippe, who will do an in-depth presentation of the objective, the challenge, the methodology that support actionable impact for PV penetration in urban area. And he will do so by trying to tackle the various use cases that we are going to develop in this session, but as well during the lifetime of the project, and try to target the various stakeholders' needs. So basically, there's many of you who have maybe different need using maybe the same type of product, and this is what we would like to assess. Then we will present you the tool to support this use case of high PV penetration. And it's a combination of open source, open platform, open data, standard, interoperable process component, and they are based on the Jupyter Notebook solution. So this will be something that Philippe will take time to basically show you step by step how this tool is made of. And then it will lead us to the last information, where we are going to provide you the necessary information for you to perform your personal hands-on session. So after this session, you will be provided with some information, credential to access the tool itself, and you will have basically 3 days to test it by your own. And then we will reconvene on Thursday to do the debrief. More detail to come during this part. So the eShape project. So eShape stands for EuroGEO Showcase Application Powered by Europe. So it is a project which is funded under the Horizon 2020 Research Innovation Program. And it is a European contribution to GEO, in order to establish EuroGEO. So the GEO, it's a partnership of more than 100 national government and more than 100 participating organizations. Basically, in this organization, you find key Earth observation players such as ESA, NASA, JAXA, basically the national Space Agency of Europe, US, and Japan. You find EUMETSAT, you find ECMWF. You have heard about this institution who provide CAMS registration services. And this GEO partnership want to basically support action to make informed, coordinated, and comprehensive use of Earth observation. So basically, the best practices that may basically come up in this partnership may solve and pave the way for the use of Earth observation. And this project support GEO in trying to establish EuroGEO, which is basically the regional support of GEO in Europe. So it's a big project. It's 15 million euro grant, 60 partners, 7 showcases. You see the nice icons in this slide. And basically it aimed at developing 32 pilots. That's a lot of pilots. And we are only, showing you one of them in this session. So it's a 4-year grant. So we have started last year. And it is coordinated by MINES ParisTech. So Philippe and I and my colleague from the project management team. More information are available on the website. So you see those 7 thematic areas. So from agriculture, health, renewable energy, the one we are going to talk today, ecosystem, water, disaster, climate. So a lot of various type of application potential for these 32 pilots. But all of them want to promote the user uptake of Earth observation data. So here you find the key words in this project, which are users. So the idea is to assess how those users may take and may benefit from your Earth observation data, mostly coming from European assets such as Copernicus, and in order to develop those products using co-design. So co-design, it's, let's say, maybe it's a buzzword, but the idea there is to make sure that the user are basically integrated in the full scope from the beginning to the end in the design of the pilot in order to support some economic, social, and policy value for the European citizen, and namely for those users. So you are the users, and we would like to basically invite you, this is what we are doing today, to test, to assess, to comment, to enhance our pilot. And this is the case for all the 32 pilots of the eShape project. One last thing on the project that may be of interest for you is that currently the project has saved some money to basically onboard new pilots. So currently 5 new pilots has already onboarded last year, and basically 5 new pilots will be onboarded this year. So onboarding means that you may claim a grant for 50,000 euro, as well as the support of the full eShape project. So if you have a pilot, if you have something after this presentation that may sound to you something that you would like to develop within your own environment, you may claim to be part of this new 5 onboarded pilot. And the project will provide you support for co-design, deployment, user uptake, capacity building, sustainability, communication. All the detail will be available at the eshape.eu project. So think about it if you want to maybe be part of this very big and very, let's say, powerful project in Europe.
Lionel, just may I interrupt you?
Yeah, of course, Philippe.
Yes, just to precise that this submitting for the onboarding process is a very light onboarding process, because it's not a full 70 pages of Horizon 2020 project. It's a simple way to be on board on eShape. So
it's simple and fair. We have some evaluation team. I would want to go into detail. Just mention that, this is something that could be of interest maybe for some of you. Thank you, Philippe. So I will just finish my first part by trying to provide you what I call a high-level pilot architecture and workflow. So this will be basically really done precisely by Philippe, but I would like to provide you some picture about where are located some of the key elements that you will see afterwards. So as I mentioned, we have developed, and basically the user interface that you will have to deal with in order to do the process and to access results will be done using what we call notebooks. So it will be explained by Philip. Basically, it's a kind of hybrid type of things where you can do code doing some additional text and do some process. So this is basically what we have selected as a, let's say, graphical user interface, and we have deployed this notebook into WEkEO. So WEkEO is one of the 5 DIAS. DIAS stand for Data and Information Access Service. These are 5 let's say, cloud computing resource and tool providers that basically have the mandate to provide some connectors towards Copernicus and Sentinel data. They are not the same as maybe Amazon that maybe you know already, but they are really, let's say, focusing on providing such cloud and computing resource, but they have key connector to Earth observation assets. So we have deployed this notebook on the Jupyter and the Jupyter notebook on the WEkEO. And the first thing that the Jupyter notebook will do is that it will request some time series on the CAMS radiation service. So you have been warned already that you need to have some valid credential in order to fully benefit from the end-on session to test this tool. And it is do so because the first request, which is done by the notebook, is try to access web processing service, which is already a tool which is on the shelf deployed by SoDa team to access CAMS radiation. So from the CAMS radiation, we will retrieve all scale radiation from the CAMS database, but as well aerosol and water vapor components. So this will be bring back to the notebook that will basically in parallel perform some additional process requesting additional data. So those data are the satellite-based digital elevation model SRTM, which provide horizon on the long term, and on a short term, short distance, let's say, computation of this elevation. You have the digital surface model, which is providing you a 10 up to 25 centimeter resolution digital elevation surface provided by EGN. So as a whole, when all those data will be, let's say, requested, mixed, you will then have the result that will be provided you by the tool, which is a daily profile of electric consumption and PV production in the case of self-consumption use case. So this is it. I will now either, maybe, I don't know if there is any question, I will take one, and I will hand over to Philip, who will provide you with some, let's say, in-depth information about this tool. So I don't know if there is any question that is burning or if we take them afterwards. In any case, I will stop sharing and leave the floor to Philip.
Thank you very much, Lionel. So I will restart the presentation from here. Sorry. Yes. So in the framework of eShape, this pilot is a pilot 2 of the showcase related to renewable energy. There are 3 other showcase, one dedicated to offshore wind energy, one dedicated to solar radiation, nowcasting and forecasting at country or European scale, and one new onboarded pilot about the first one was offshore, and this third is about onshore wind energy. And we have this pilot too about the high PV penetration it's in urban area. So the partners are MINES ParisTech, ARMINES, Transvalor, and DLR, which is the German aerospace. And the objective of this pilot is to develop geographical information system tools for the high photovoltaic penetration at urban scale, providing first Earth observation-based information about urban energy system, modeling, for example, the electric energy demand profiles from different blocks of the city, and also to provide with accurate electric production of fleets of ensemble of PV rooftop systems. The expected users community are urban planners, grid operators in the city, aggregator for energy trading, and of course, citizens for self-consumption, and researchers in energy and urban planning. In fact, this pilot is divided in two parts. The first one that will be presented partly to you is the ARMINES part, based on the PV variability at urban scale. And this pilot is implemented in Nantes, and we have and we want to see how to upscale this pilot to another city or another country. And this is challenging because of mainly the resources we need about the digital surface model at very high resolution. And we have the DLR parts, which is about the Earth observation data from Sentinel-1, for example, or Sentinel-2, radar system or multispectral systems for PV integration in the urban energy systems. And the pilot is centered in Oldenburg in Germany. So, and we, as said by Lionel, we are using the DIAS WEkEO. Okay, so for this, the parts of ARMINES in the pilot 2, we are dealing with something starting from what is already existing, which is a solar cadastre. And so this solar cadastre is the one provided by in an operational way in France and in Spain. I think no. It's the solar cadastre provided by INS and WeTrust. And we are at the origin with Transvalor of the algorithm and the operational chain of processing to provide cities and a group of cities with solar cadastres. And these solar cadastres, once created, are operated and disseminated by INS and WeTrust in their own web services. So you can look at INS and WeTrust .solar website, and we will see different places where the solar cadastre is existing. And basically, in terms of information about solar resource, because we are in solar trading, basically it's a static map at high resolution, here 1 meter resolution, looking only at the roof tops of the city. So this is this one, and providing with yearly irradiation on tilted plans. And each square you can see here, each pixel on this map corresponds to 1 square meter, integrating the shadow from the surrounding, so the shadow from the digital elevation model, and the shadow from the buildings, from the superstructures on the rooftops, and from vegetation that has been acquired during the campaign of the digital surface model. So it's a mix of Copernicus atmospheric monitoring services radiation and the information about the shape of the urban area. And from that, you can have this map, and then you can have some application to see if your rooftop is indeed of interest in terms of financial analysis for installing a certain quantity of PV module on your rooftop. And the business model of INS and WeTrust for this solar cadastre, which is static, is the relationship they are making between the clients that is looking at this solar cadastre for free and the PV developers that want to develop PV rooftop systems. Once the users has clicked on the roof, he has the opportunity to check and to choose a PV developer that has been screened out by very drastic criteria of quality by INS and WeTrust. And then if the deal exists between the user and the solar developer, then INS and WeTrust will get paid by the installers. Sorry. Okay, so this is already existing, and this tool is what we say is TRL 9 because it's fully operational. And the pilot 2 is coming from this solar cadastre to something that's try to have a description, not only the yearly irradiation on average, but talking about the solar variability induced by the PV systems on the urban area. So we want to have something that is dynamic and to provide with information not only on the average, but also the profile of production that we will compare with, for example, the consumption. Okay, so what are the data and the infrastructure we are using? So, as I said, as a summary, we are using Copernicus Atmospheric Monitoring Services, CAMS, accounting for aerosol water vapor, to provide with all sky irradiation, so CAMS-RAD. We are using digital elevation model, SRTM. We are using digital surface model coming from the French Geographical Institute, IGN. And we are also using, not in this pilot, but we can use the building footprints to locate the roof. In terms of infrastructure, we are using the DIAS WEkEO, as introduced by Lionel, to provide with two things: the back office, to provide the cloud processing as requested to compute on the fly the solar information at high resolution, and the front office that you will check and test for the coming days, to host a Jupyter Hub with Jupyter notebooks and to exemplify different use cases. And in that case, we will exemplify one of the three use cases we want to develop within the project of eShape. Okay, so the first one is the one that we will look at it today, is about the PV self-consumption. So it's about sizing individual system. And we want to not only see how many irradiation I get at a yearly basis, but what will be the synchronicity between the PV production on my roof and the electric consumption for my building. So first, we can have selection of a roof, a given roof. So on the fly, you can get the information of PV production, and we can compare it with the electric consumption that can be provided by the users. For example, if you have in France, if you have a system to electric metering on your house, like just Linky, you can get your own consumption and to compare your own consumption, for example, for 1 year with what would be produced by your PV system, including the weather variability, the cloud variability, the aerosol variability, but also, of course, the shadow-induced variability, because you are on urban area, and this shadow is very important to account for, and the tilts of the modules, of course. The second use case we have in mind that won't be presented today as a test is to be able to simulate PV injection in different source points within the electric grid for different scenarios of PV penetration. In that case, the targeted user is not the individual citizen, but it is the DSO, distribution system operator, that just like in France, ENEDIS. And for example, in this blocks of 1 kilometer per 1 kilometer, we have a certain number of injection points in the grid. And for different scenarios of PV penetration, we can simulate the amount of energy that with the amount of power, maximum power on each source points. And then thanks to the simulation, we can provide with also the time series of PV integration in a source point, which is very important for the DSO, we believe, because of the problems in the electric grid to cope with a certain variability and a certain amount of energy injected in the grid due to the PV development, depending on the amount of PV you get on the rooftops. This is the 20% here, for example, meaning that 20% of the surface of the building will be implemented as a PV rooftop system. And thirdly, we want to develop also use case that is about the PV nowcasting. So here in the two previous, it's about the variability induced, and we are for that using historical data sets to get the variability and to get some statistical analysis of this variability compared to the consumption or in terms of variability in the PV electric grid. And here we are interested in the PV nowcasting for a set of an ensemble of fleet of PV rooftop systems. And the users we are targeting is, for example, energy trading for people who have a portfolio of PV rooftop system in urban area. And we have in mind, for example, in France, we want to contact them, Urban Solar Energy, which is electric provider based only on PV at urban scale. So in that case, we are mixing solar forecasting as presented by Yves-Marie Friday, using cloud motion vector, and of course, taking into account also the 3D shadowing effects from the GTL surface model. So we are mixing two sorts of variability for the future because it's very important, the two. And in that way, you will be able to provide with nowcasting and forecasting of the PV production of the sets of PV rooftops using the techniques of CMV and mixing of the 3D shadow representation. Okay, this is for the three use cases we have in mind for the pilot 2. And before starting the presentation of the Jupyter notebook about the use case, the self-consumption use case of the pilot 2. First of all, as you know, in the registration for today and for the testing for the coming days up to Thursday, we need, of course, since we have in this example some request on CAMS radiation, we ask you to register on the CAMS website for free in order to be able to do this web processing services to request CAMS radiation dataset. And as a joke and just an optional exercise, since you are registered, we have asked you a sort of exercise to look at the way you are getting information on the website soda-pro.com. So the question is, for this latitude and longitude and elevation, the value of 1 hour direct normal irradiance, both in all sky and clear sky situations, at noon true solar time for the day of the 8th February 2020. So I don't know if someone has tried to get the answer. So maybe people who have the answer, maybe they can. Did someone try to do this exercise? You have maybe? No? Okay. So this exercise was a little bit tricky because first we have to locate the...
Excuse me, Philippe. You have
yes?
an answer of Maria. Maria, no,
okay.
excuse me. Marie, excuse me.
Marie.
On the discussion tool. Not Q&A, but discussion tool. She
I don't
writes.
see this.
She downs the exercise.
Ah, okay,
she
good.
just says me with a smile.
Me. So okay. What's the so okay? Good for you, Marie. I hope that it was fun for you. And the idea there is a trick because we have first to locate the noon true solar time. And to do that, you have two choices, or using the tools we provide you with for the basics and the true north localization, you know, the Excel tools. And another way to do that is to use the web service here, for which you can get not only the all sky and clear sky estimation from CAMSRAD, but you can get also the top of atmosphere at horizontal at horizontal plane. And this is the blue line here. And in that way, you are sure that if you are locating the maximum value at this point, it is true, it's 12 true solar time. And if you look at this, it corresponds to, in universal time, to 11 hours, 47 minutes. So, and the question was about the 1 hour average of direct normal irradiance. So the best way to do that is to get 1 minute data sets and to locate the data between 10 hours, 48 minutes and 11 hours, 47 minutes, which gives you 60 minutes, 1 hour. And if you are doing this average for this time interval, then you will get the clear sky 1 hour direct normal irradiance 738 watts per square meter. And for the whole sky 1 hour direct normal irradiance, you will get 378 watts per square meter. So Marie, did you get the same values? Okay. So if you have any question about this optional exercise, do not hesitate. We will ask this offline maybe. Okay, so we can go on. And okay, now it's about, there is a conversation. Okay. Yes, there are 3 tricks. The first one is not at universal time in true solar time. The second one is 1 hour and not 1 minute. And the third one is to look at the normal irradiance. Yeah. Okay, good. Anyway, it's good. Thank you, Mary. So I will show you now the connection to the Jupyter Hub to get the Jupyter Notebook and to get some comments online with this Jupyter Notebook about the use case of PV self-consumption in Mars. So I stopped my PowerPoint presentation and go to the, so it's a demo, on a live demo, so hopefully it will work. So I am connecting one of the username that will be delivered to you after this presentation. So I'm connecting in this Jupyter Hub. Okay, so nothing is computed on your laptop or your desktop. Everything is computed in the WEkEO. Not only the computation we will use, we will have in terms of solar cadastre, but also in terms of Python codes for the pilots. So I have a folder here I have to follow. And I have different files. And we can use this as a explorer to look at the data we have on this folder. And the one that has the Jupyter Notebook is this one. So I get this one. Okay. So a Jupyter Notebook, in fact, is a very nice hybrid document. So it looks like here a Word document because it's mixing true text, and you can have some nice word processing of the more or less word processing, but also it mixes with blocks of Python codes, and each Python codes can be run independently for each block, each cell. Here, it's a cell, it's another cell, etc. And when I am running this cell, something happens. Sometimes there is nothing because it's only about initialization. This one is only about the initialization of the different libraries we will use in the Python code. So it is very useful, and it's requested to launch this cell before launching the others. So it should be run one cell per one cell in the right order. And for that, I will explain this afterwards. And you have some cells that are only some nice text, and there is nothing to do. And you have some cells that are providing with some outputs. So each cell can be run cell per cell using this button. So it's exécuter en français. Yes, by the way, you have also something very useful to have an overview of this document, is to have this button, which provides you with the table of contents of the documents. Thanks to this table of contents, you can look at the plan of the documents. So we can see here that there are 3 sections. Each section are decomposed in 2 or 3 subsections. So the first one is about the definition of my zone of interest. The second one is about the selection of the PV surface I want to simulate. And the third one is about the main interest, is the PV self-consumption. Okay, so, and I can look at the different sections just by clicking it. Okay, so now start with the first cell. Do not forget to run this one because it's an initialization. So I get this, okay? And what you can see is while the cell is running, you have a star here. And when it's finished, you have a number. I can restart this and it will increase the number, okay? So, and if you want to restart from the beginning, you can use the kernel restart and clear outputs that I will do here to restart from the beginning, okay? So I can do this, so you can see the star and then the 1, meaning that the cells has been run, it's okay. I can go to the third one where I have something to run, so I run this. And once I have run this, I can see something new where you can here see the nonce city. You can see a green zone, it's a polygon here, a large one. And the pilot is only focused on this area because of the amount of data we want to upload to the server. So we are just for the pilots, we limited the zone in a zone large enough to see what happened. And there are different type of urban areas. So you have different types of PV variability you can test. And if I look closer, I have already, for the purpose of this exercise, I've already selected one polygon, and for the beginning of the test, I will let it like this, and I will show you afterwards because it's already computed, and not to spend some time waiting for the results. I assume that I have selected this building, but I can also select something that is not a building. This is new because it's open polygon, okay? And you have to select also the first year and the last year of analysis, and here for the purpose of this already computed things is 5 years starting in 2015 to 2019. And also I have to say that 2 things to limit the load of computation. We have limited the surface to 1,000 square meters. Okay, so if you are selecting a polygon larger than this limit, the computation won't be done. Okay, and you can select a large time range, but we prefer that you do not exceed 5 years of in a row of computation. It's not forbidden, but if you want to have something in a reasonable time, it's better to select less than 5 years. You have to don't forget to set your email address that has been registered in the CAMS radiation sites. Okay. So this is registered. So I can move and select the second this cell. So I've used a shortcut, very convenient shortcut. Is instead of clicking this button, I can do control return. Okay, control return. So control return says that I have selected a 207 square meter polygon. So it's okay, it's below 1,000 square meter. And then this section is about the computation of the 5 minutes, every 15 minutes, sorry, maps of global tilted irradiance, sorry, at 1 minute resolution, 1 meter resolution, and 15 minutes resolution, starting from the first year you have selected and the last year you have selected. Okay. So there are a mechanism here to prevent you from running with a large polygon here, and also if you didn't set properly your username, otherwise you get an error afterwards. Okay. And then something that's okay, you should know. There is something, the result file is already existing for the purpose of the demonstration. So this file is already on the folder here. Okay. So if I run this cell, in fact, since the file is already existing, there is no computation. So if you want to use a new computation, you have to change the name of this file, name, and run the cell. And then the first time you are using this cell, it will send a request to the WEkEO cloud computing server to get the computation done on your polygon for the time range you have selected. Okay. And of course, if you do not change for the next time the name of the file, then it won't be computed. It's only using the already computed one. Okay. So I use this cell again. So nothing happened in terms of web processing services, but I have a recap saying that I have selected 5 years. Okay. So now this section helps you to look at the data that has been provided by the computation. Okay, I will start with one example, and I want to see as a time series and as an image what has been computed. So here I can choose the first day of computation. Here I am choosing an easy way, the 1st of January of my first year, 2015, and the number of days. So for the first example, I will have only 5 days of visualization. So I do the run. So I have something that is between these two dates, right? And I have the first image providing you with the irradiation on the tilted plan with 1 square meter of patches over the time range expressed in kilowatt-hour per square meter. So what we can see the shape of the polygon that has been selected here. Each polygon, each square corresponds to 1 square meter of irradiation integrated in 5 days, sorry. And we can see clearly that there are 2 free zones, in fact. A first zone located towards the south, a second zone located with a slope locating towards, let's say, more or less towards the north. And we have something that should be sort of flat roof, I think, because the level of irradiation in that area is larger than this one. Okay. And we have some variability within the roof because of the shadow nearby or in the roof itself. Yes, we have a question. What is the transposition model that is used within shape? Okay, it's a transposition model based on the Perez model, including the shadow effects. Okay, so there are some assumptions about the way the radiance is decomposed in terms of direct components, circumsolar components around the diffuse component around the sun, the horizon diffuse and the isotropic diffuse. And for each component of this diffuse components, we are providing with the model of Perez model and do the sum to get the global tilted irradiance, including the shadow. And of course, sorry, each 1 square meter is oriented. And the orientation is computed from the digital surface model. I hope that I have answered the question. Etienne, if you can skip the question after the answer. Okay, okay, thank you very much. Okay, so this is for the time range I have selected. I have an average as an image, but I can also do an average in space and look at what happened in time. So here I can see the 5 days I have selected, average on the whole rooftop here, okay? Every pixel I have selected in the polygon, even pixels that are not very good, yeah? And I can see the variability day by day in January, and I can do it the same, for example, in summer time. In summertime, we have something like this as an image, but we have also something different in terms of time average over the space. Okay, so now I can look at this same information, but for 1 year of data. So this is the results in 1 year of data. So the maximum irradiation I get at a yearly basis is more than 1,400 kilowatt hour per square meter. And the lower values is lower than 600 kilowatt hour per square meter. Okay, kilowatt hour per square meter. Okay, this is very important because we will use this information to select eventually the PV module I will want to install in my simulation. And as time variability, you can see 1 year of data average out for the whole pixel here, corresponding to, by the way, so we will see the square meter of this surface afterwards. Okay, so we have here seen the results of the WPS, which is a matrix of global tilted irradiation every 1 meter in the bounding box of the polygon I have selected every 15 minutes in the time range I have selected. So it's a large amount of information I get. And this is a way to first look at this information. Then I want to do a simulation of the PV rooftop. Of course, it is rational to think that I don't want to install my PV system in places where, in the square meter, where the amount of energy is not enough to be financial plausible. Okay, so I have something to do for that. First, I want to first select a type of PV efficiency. So in my simulation, I have used something that is standard, not the best we can get, but not the worst also. And for the PV module, we have selected an efficiency of 18%. So I select and I get the efficiency. Then I have a module computing the amount of energy I get above a certain threshold and the surface I get above a certain threshold. So for example, I will, oh, sorry, there is a question. Yeah, Right, it's a good question. In that, sorry, I will read it. You are interested in GTI with the same angle as a rooftop. On the flat rooftop, the standard installation angle for our PV system would be 15 degrees. Yes, you're right. In Germany, it will be that. Yes, it's a good point. For the moment, we do not distinguish rooftop that are horizontal and rooftop that are not. Meaning that we are just looking at places where it's plain, where it's flat, not horizontal, and we are providing with simulation with the same slope as the roof. But you're right, we can force the computation to say, okay, I override the tilt and orientation of my PV panel, and I can do the simulation in the same way. But yeah, in this pilot, it's not possible. Yes?
Philippe, I just want to make a remark. It is historically from the way the solar cadastre has been created.
Yes.
I can talk about this because I was in charge of the operational creation of the solar cadastre. And we defined that in France, it was created for France, and in France, most of the cases for residential solar installations, PV panels are either part of the roof or on the roof. So we made some treatment of the DSM for computing the locations where the roof was flat with a specific angle, and or basically we use the tilt azimuth of the roof for computing the PV, the GTI, the global tilted irradiation.
Exactly. So thank you very much, Etienne. Okay, so what I have in mind is, okay, I want to select, there are many ways to select my square meter where I want to put my PV system. A very simple way to do that is saying that I will select a square meter for which I have a certain level of yearly irradiation. Okay, it's rational to do that. So the idea is, okay, starting at this threshold, I want to have an idea of the amount of surface I can get for a certain level of yearly irradiation. So a certain level of quality of my rooftop. So with this computation, you can look at the results, and for different thresholds of the yearly irradiation, here starting at 100, 1,200, and up to the maximum value, you get a curve here indicating you the amount of PV system in square meter you can get for a certain level of minimum of yearly irradiation. Okay, so if I look at least 1,400 kilowatt hour per square meter as a yearly basis, I have, let's say, 70 square meter of effective surface on my roof. Okay, so I can select this value here. So I can select 1,400 as a threshold, and I can run the computation. And it says that, okay, my surface I have selected is 69 square meter. It corresponds to this area here. So compared to, to this one, which is the whole data set in the polygon. So I have selected a subzone only on the basis of a threshold on the yearly irradiation, which is quite rational to do that. Okay, so once I have set this, I assume that I have put all my square meter of PV system covered by PV modules. Okay, it's an assumption also, because of course the PV modules have a certain place, so we can play with the optimal tiling of the 1.62 square meter of PV in this, but it's too detailed for the such analysis, I think, we assume. Okay, so since I have selected this amount of PV panel, 669 square meter, I get install PV system of 12.4 kilowatt peak. Okay, so I have now at this point, I have selected my polygon. I have selected a zone on which I want to install a certain type of PV system. And then I can do the simulation of PV production. For this simulation, I need the irradiation, and I need also temperature. And this temperature, in that case, is coming from MERA2. MERA2, as presented in the previous session, is I don't remember. Sorry. Can I help you, Etienne? It's a reanalysis product. Sorry, providing with different parameters, meteorological parameters, including the temperature.
Yes, I just cut my mic was not on. Okay. So but you made it. Okay. Sorry.
Okay, thank you very much. Okay, so once I have once the PV production has been done, we can also look at the production, and here it's an example on the to select 5 days here in June to see the PV production. Okay, this is my PV production expressed in kilowatts. Okay, so in June, and this is at 15 minutes, and this is the average at the sum at the monthly basis for the different years I have selected. If I change here the M by Y, I get the same, but at the yearly basis. So I get 5 days, 5 years. And I can also select it at a daily basis, which is quite simple thanks to the Panda data frame for people who are familiar with this type of things. And this is the daily production of my PV system for the 5 years I have selected. Okay. So we have selected the polygon. We have done the PV simulation. Then we want, since it's a PV self-consumption, we want to do analysis compared to the consumption, electric consumption. So in that use case, we don't have real, unfortunately, we don't have any real electric consumption for this area. So we have used a library, DemandLib, and Romain Bessot has developed a code, thanks to DemandLib, to provide you with the analysis between the PV production and a profile, yearly profile, 15 minutes profiles for a typical year of electric consumption. And you have in this library different profiles of consumption here. So you can have a household consumption, commerce general, industry, etc., etc. Something that is not very, a farm, maybe a farm in a city, you can check it. So in this example, I have selected the H0 household profile. It's only a profile, so you have also to select the amount of energy as a yearly basis, because to scale up this electric consumption profile. And for that, I have selected average power of consumption power as a yearly basis. So here it's a 5, for example, 5 kilowatts as an average. And if you want to have the amount of energy as an average, as a sum, within a year, you have to multiply by the number of hours we have in 1 year, except for the leap year. And then, thanks to that, we can here compute the different years of PV production and compare to the typical year of consumption. So this is a loop here for different years of analysis. And we can do the computation here. Should be fast. Okay. So we can see that I am consuming in a year more than 43 megawatt hour. And this is here 2 box plots providing with the variability, the interannual variability of the PV self-consumption and the PV self-sufficiency ratio. So what is the PV self-consumption ratio? It is the amount of energy coming from the PV system that is actually consumed because it's below the energy consumption, divided by the amount of energy that has been provided by the PV system. So here I can see that it's very stable because less than 2% of difference from year to year. And I have a self-consumption ratio of approximately 87%. So 87% of my PV system is indeed consumed by my building. And my PV self-sufficiency ratio is the amount of energy I have provided from the PV system compared to the full energy consumption. Okay, so it means that it's very stable as well. It means that 30% of my energy consumed in 1 year has been provided by my PV system. So in one glance, you can see the efficiency of the PV self-consumption compared to your consumption. You can now get a detailed analysis at this point, a detailed analysis for one given year. So for example, I can select the last year of the data. So I redo the simulation of the consumption here. And I can look at, this is the profile of energy consumption at a daily basis expressed in kilowatt hour. And you can see here, as an household, you have a seasonal effect, of course. You are consuming less in summer than in winter, of course. And because you are eating in that case, there is a household eating with electric system. And you have variability from 1 week to another within a week because of the weekends you are still in house and the working day for which you are not always in the place. Okay, so here it's an example of 5 days to understand what is going on in terms of PV production and electric consumption. And you can, of course, change. I can do the same exercise looking at the month of February. Okay, I prefer to have, because you have some overproduction in. Okay, this is an example here. So in blue, you have the energy consumption at 15 minutes basis, and you can see 5 days of electric consumption. So up to, I forgot to do that, it's expressed in kilowatts. Okay, and here you have superimposed the PV production, okay, 5 days of PV production of my selected rooftop. Of course, when the PV production is below the energy consumption, then I can say that I have consumed all my PV production. Okay, and I have to compensate to import this amount of energy from the network to provide with my requested energy. But sometimes you provide with more energy from the PV than you are able to consume. Since in this scenario, we do not have storage, then this amount of energy is a surplus, and this surplus can be sold, at least in France, in the grid. So you can export this energy. Okay. So the self-consumption is the ratio between the energy below of the red curves below the blue curves divided by the area of the red curves. And the self-sufficiency is the energy I have provided divided by the sum of energy I have consumed. Okay, so you have here some definition of the self-consumption ratio, etc. And then you can do a computation, and you can see that, okay, in that year, I have consumed, let's say, 43.8 megawatt hour. Okay, I have produced 15 megawatt hour, but only a part of this production has been indeed consumed by my house, and this part is 13 megawatt hour, corresponding to 86% of my PV production. Okay, I have a surplus here of 2 megawatt hour, and I have to import from the grid 30 megawatt hour. Okay, so we can see here the ratio of self-consumption is 87%, and the ratio of PV self-sufficiency is 30%. Of course, if I would have a storage, I will be able, but in that case, it's not very a large amount of energy, to get this energy consumed as well in the next time. Okay. Okay, so it's a way to assess the self-consumption. You have all the figures, and of course, for the clients, you can say, okay, I am buying my electricity at a certain price. My PV production, since I have this for 20 years or more than 20 years, as a level life cost of electricity, it is this cost, okay? And when I have an export of PV electricity, I can sell it at another cost. Having these three figures in mind, you can have a financial analysis to get if it's interesting for you to do the self-consumption or not. And also you can also, following the methodology described by Romain Bessot in his PhD, you can provide with LCA analysis, life cycle analysis, based on this self-consumption, and to provide with the interest of having this PV self-consumption in terms not only in financial analysis, but also in terms of environmental impacts, including the CO2 impact, the climate change impacts. If you know the mix of energy in your country and the LCA analysis of your PV system, including the way you are providing the system and the way you are recycling the system. It is another story, but we can discuss about this. Once you have these overall figures about the self-consumption, you can have the pleasure to look at the data at a monthly basis. So it is here, from month to month, you can compare the amount of energy you are providing from the PV, the amount of energy you are exporting, and the amount of energy you are consuming year, month per month as an average. Okay, so we can see here that in November, the amount of energy you are exporting here is very small, and you are consuming all the PV production. And maybe it's a way you can say, I can increase the amount of PV system to reach this level, maybe, to improve and to optimize my system in terms of financial part and also in terms of environmental parts. And you have the same at a daily basis. So you can see, you can compare the PV production and the energy consumption, and you can distinguish the amount of energy you are consuming and the energy you are exporting. And the same at the monthly basis, which is a nice figures to look at, and you can say, well, this is the profile of my consumption, and this is the part of my consumption I have to buy, the part I have provided by my PV system, and this part is the one that has been exported by my system. This is, if this one is too large, it means that maybe storage is of interest for you, maybe, but you have to take into account also the environmental impact of the storage, which is a part of the PhD and the book from Romain Besson. Okay, so I have passed the whole notebook, and I want to finish by an example of selecting a polygon to do my, if you want to do your own simulation on your own place you want. So I can restart here. So I am here and I want to select one polygon. So I can change completely the place. For example, here I can look at, I don't know, voila. Sorry. Okay. I can look at this place, I don't know. And I can locate this polygon here. I have to finish by the first point of the polygon. So I have selected my polygon. For the purpose of this demonstration, I only get 1 year of data. Okay. So I have this polygon selected. I changed my name because otherwise there won't be a recomputation and there will be a problem between the years, etc. So my zone, for example, here. And when I do that, I will send indeed a request on the web processing services. So it is in real time. So it's running. And meanwhile, maybe Lionel, you can do music to wait.
Like it?
Yeah, it's a perfect
okay.
elevator music. Okay, it's yes, it's done, and I am downloading, so I can look at the file explorer, and I can see here my new HDF5 file that you can download desktop by selecting this and do a download. Okay. And I won't redo all the notebook, of course, but just to look at the results, I have this results as a yearly basis. So here you have clearly you have two zones. Here, higher level and the lower level, and you can do the PV assumption and the PV simulation. Okay, so that's all for me. I stopped the screen sharing to give the hand to Lionel for the conclusion. Thank you for your interest and attention.
There's a question, Philippe?
Yeah.
Can you?
Okay, I didn't see it, sorry.
Yeah, just now.
I don't see it.
Okay, from Jonas, can I integrate the PV production and house consumption curves into these notebooks to compare the efficiency of my PV plant to the actual weather data? And can I get all the financial results for my PV plant?
Eventually, we want to have this. Here, it's a real, by the way, it's a simulation because it's a simulation from CAMS with certain type of PV system and a profile, generic profile of electric consumption. But if you are interested in having a real case and you have indeed a file with energy consumption in your place, then you can do exactly the same type of analysis with real data. And you get from the code from Romain, very fine analysis of your PV self-consumption up to this type of table. And if you have real value of electric price on the network, the levelized cost of energy of your PV system, and the cost, the price of the PV surplus you can sell to the grid, then you can go to real, quite accurate, we hope, financial analysis of your PV self-consumption. I hope that I have answered the question.
So there's another question from Aurélien Gossorg. Thanks for the presentation. I did not catch the information. Where does the tilt angle of the zone of interest is taken from?
It's a good question. It's taken from the digital surface model elevation itself, because it's a very high precision. We didn't specify, but in Nantes and in many cities in France, we have the chance to have 10 centimeter digital surface model. And thanks to this 10 centimeter resolution digital surface model, we can provide with, for each square meter of analysis, a very accurate analysis of the orientation and the tilt of each square meter. And this is this value that is used for doing the computation. And it's a remark from Jonas saying that in a rooftop that are horizontal, maybe it's good to have to force the computation to say, I don't want to have horizontal, but something that I want to specify. And you can have, you can imagine to add in this notebook to have an option saying that I want to force the azimuth and tilt of the PV module I want to simulate on my roof. But in that case, it's coming from geometrical analysis of the shape of the building.
Thank you, Philippe. So both Jonas and Aurélien, thank you for your response.
Okay, good. Thank you for your question. So I stop the sharing and I leave you the floor.
Okay. Thank you very much, Philippe. So I will share. Okay, so can I share my screen? Yes. So I think you can see my screen now. Do you?
Yes.
So we'll put it in full mode. Hopefully it will go. I guess it is in full mode now.
Yes.
Thank you, Etienne. So first, Philippe, thank you very much for this really outstanding presentation. Definitely, I participate in the building of this pilot, but yeah, really great. You really do good at illustrating both on the slide and then on a step-by-step Python notebook. And I think all the powerful possibility of this approach using Jupyter Notebook. I would like also to congratulate my colleague Romain, who has been mentioned by Philippe. You have the list, Benoit and Raphael, who they really do a tremendous job to put all things together. So you see that not only we have some front end in Jupyter Notebook that represent a lot of let's say lines of codes, which has been really tested in a rush to be ready today, but you have also some assets that came from the services which are already existing and in operation mode by Transvalor, the WPS, which access the consolidation data. You have all the work from Romain on this PhD thesis, and you have all the IT support. So making sure that and Benoit and Raphael has really support us to make sure that all this IT stuff being transferred and properly working on the WEkEO, which were new to us as well. So yeah. Thanks to all of you. So now you see that this notebook is ready to be tested, and this is basically the purpose of what we'd like to offer to you now. So right after this, the end of this session, we will provide you with some instruction to run what we call a hands-on session. So This is something that we would like you to do, basically to help us to test by your own. So Jonas has made a question that was the transition. What if I do something I want to? So the so-called notebook is designed in a way that you can basically, let's say, test it yourself, take some pieces, continue the development. So it is up to you and up to your, basically your will, your business activity, your expectations. So you can do whatever you want. You will never break something. And basically what we would like to offer you now is to do your own testing. So as a first mandatory parameters for you to be able to run this test, you need to have this so-called valid CAMS radiation account. So again, it is free. It is available online on the SoDa website. I'll circulate some email and some recall for doing this. So if you want to test the notebook, and run all the full scenario, you need to have a valid free account that may be delivered online on the CAMS radiation SoDa website. So this is mandatory. Then for you, we have created some individual repository. So all the attendees, and currently we have reached the numerous clauses of 40, because currently we have set up 40 individual repository. They have been created for you and they are waiting for you to connect. In each of these repository, we have basically duplicated the notebook that Philippe has presented. So you will see exactly the same. By the way, I think that I'm sure that this session is recorded. So hopefully we will be in position maybe to provide you with the link to the record session, and especially the section for Philippe, who, if you have any doubt about how to deal with some parameters, maybe you will find your way using this recording. So you will receive this all this instruction to connect. So you will have the URL of the website, you will have your credential, and how to connect to go to your own repository where you will get the Jupyter notebook. So what we would like to do is for you to be able to test by yourself. So again, to make modification, enhancement, anything you might like. Again, you will not break anything. And we would like you to do this until Thursday, February 11th, so 3 days from now. And on this Thursday, you know, and some of you have registered, maybe not all of you. So Mathilde will basically receive some new, let's say, requests to attend this debrief session, where we will reconvene for 1 hour. And what we would like to do during this hour is to try to get your feedback, basically, about your experience in getting access and on this ended session, getting access to the Jupyter notebook. As you know, we are, because I presented earlier, we are part of a European funded project, and there are many other activities that we are going to run in conjunction with Transvalor in order to assess the product based on the use of this product by users, stakeholders as you. And to that respect, I would like you to make sure that you can fill a small questionnaire that we are going to basically wrap up now. So you can do so, and you will do so by email. I will send those questions in the bulk of the email that will be sent with the instruction. And basically, these are 5, not simple questions, but only 5 questions that I would like you to answer. So the first one is, what is your opinion regarding the final product? So the file that you will get as a result, about its quality, interest, relevance, what are the possible enhancements, and what is the future possible usage and exploitation that you may be interested of. So again, these are open questions. You can basically reply in the bulk of the return of email saying what you think about this. Then I would like to ask you, what is the value, the added value for your activity, having access to such service? What does this tool and the result it delivers may be of interest, offering you new opportunities and possible actionable knowledge or business. The third question is your willingness to pay for such service. So as you know, these are products that has been developed, and you see the large amount of resource that it is based on, about not only the IT, but the amount of work that need to be set up in order to provide such tools. So again, this is something as a natural flow from R&D to on-the-shelf product that may be of interest for you and delivered by Transvalor. And Transvalor, you know, delivers product for the community, but as well product for pay. You're sure maybe already buying such products. So what will be your willingness to pay? So I don't ask you to provide me a price. It will be something that we will assess in the course of this project, but basically your willingness to pay. Again, free comment here. What maybe will be the other draft product features that will be useful and beneficial for your activity? So think about the presentation of Philippe about the two other use cases that he has presented, not only the PV self-consumption, but the one that deal with forecast and the one that deal with DSO. So maybe you're in this under this activity, and we are really we would like to listen from you. And finally, what is your opinion regarding the Jupyter Notebook? So once you will be connected, do you like it or not? Does it bugs? Do you like the performance or not? Do you have any difficulty, suggestion, announcement again? So it is open to any of additional comment. So this question again will be part of the email with the instruction to connect. And I really ask you to take some time to fill this questionnaire, because it will definitely support the global approach that we have in trying to do the so-called co-design with and for the users. Again, this is something which is a marker of our project. We would like to hear from you. You will basically be in a position to pave the way and to shape the final product that we may be in a position to deliver. So thanks again in advance for your willingness first to assess and then to answer this question. So I think that's it on my side as well. I don't know if there's any additional comments or. For
the moment, I see nothing.
Okay.
In terms of. No, there's a question from Marie Musielkova. Is it possible to do similar simulation for places which are not in France? Sorry, they asked that question. I did not catch this information. Sorry.
So we would like to have this. It is in the framework of eShape, we will investigate the possibility to go to global. And of course, the main problem we are, thanks to the work we are doing with Transvalor, we are providing the solar data in the pretty good surface. But the main source of information we need to do such analysis is the digital surface model, because the digital elevation model is existing worldwide and for free. So the main problem for this type of computation is the digital surface model. And not all the countries have at their disposal such information with a resolution that is acceptable for such computation. So we are looking for submetric digital surface model, and better if it's lower than 20 meters. It could be from aerial photography, could be from satellites. It's, for public non-military satellites, the resolution is, I think, a little bit too low. Yes. And you have also a source, very interesting source of information is the LiDAR. So the lights, laser detection and ranging. Laser lights, I don't know, remember the LiDAR, the acronym, whatever. So it's a way of measuring with the lights, with the laser. And thanks to this technology, you may have a good assessment of such solar cadastre, even if you do not have the digital surface model lower than 20 centimeter resolution.
To go in your direction, Philippe, we did it for the town of Strasbourg in France, using LiDAR data and interpolating it to a submetric digital surface model, but with extrapolation. But it's very good quality. Even
Yeah,
if you
it's
have
good. It's better
less,
than
even if it's less precise in terms of the number of points.
it's
The
faster.
only drawback is you need to clean up your LiDAR surface, because you may have hits on the facades of the buildings, or under a balcony or things like that, which are creating some, needs a bit of processing, but that's not the end of the world. And there are some cities in Europe where LiDAR information is available. Okay, but it's some kind of work. So don't minimize the amount of work which is involved in treating the information.
Yeah, right. But we want, yes, and we think about a sort of global source of such digital surface model is the model they have from Google Earth. And Google Earth has all the big countries, main big countries has a pretty good digital surface model, and maybe can be a very interesting sources of information for doing solar cadastre anyway. But for the moment, for the pilots, it's only located in the green zone within Nantes. It's a part of Nantes. We have, by the way, the digital surface model in the community of Nantes, which is more than 30 kilometers per 30 kilometers, which is a big zone. But for the pilots' purpose, we are limited to the green polygon I've shown you. There is a question about camps. I don't know.
Yeah, this
Yes.
is a question for the IT team to basically unlock.
Mathilde, please, Jonas, just send a direct email to Mathilde.
Just to put some, let's say, some extension about the question about Marie. I think it is also part of our, let's say, reflection about the scaling and the sustainability of the pilot itself. So not only it will be, as mentioned by Philippe and Etienne, some let's say resource, making sure we have the proper resource to run the pilot itself, but all the other aspects ranging about putting some enough IT, let's say, storage to make sure to accommodate all those data, as well as the potential, let's say, cost and potential price assessment that may be sustainable for such product will be assessed. So it's a good question, and definitely we will. So even though the current testing phase is restricted to the Nantes city, the city of Nantes, definitely this is something we are going to carry on.
There's another question from Jonas. Is this data real time? That means, can I use this program to forecast? What forecast horizon do you offer? I'll let you answer, Philippe.
Yes, it's a very good question, and we plan to have as a third pilot in the coming years of the eShape program to have a third pilot, a third use case for the same pilots, dealing with this no casting and forecasting. And so the no casting will be limited by the time rate, the frame rate of Meteosat, which is 15 minutes. So it will be something as a no casting at 15 minutes time scale. But we can reconstruct within these 15 minutes with a CMV, cloud motion vector analysis. So we can provide you with, we want to provide you with, let's say, 5 minutes up to 2 or 3 hours, let's say more 2 hours, based on CMV, mixing the information from the solar cadastre. So, but it's not possible in this example, but at a time, within the eShape project, we will provide with this type of information, yes. And we think that maybe Jonas, you maybe talk about your interest about that. We are interested in your interest because we think that for energy trading, of companies earning or renting some PV rooftops, ensemble of PV rooftops. We think that this type of information can be very of interest. And we have the feeling that you would increase the quality of this nowcast if we add, in addition to the satellite estimation, some information coming from some PV system, maybe not all, of course, but some PV system on the urban area, providing you, providing us with nowcasting at some points of the urban area, mixing it with the satellite estimation to remove all possible bias in the nowcasting and forecasting. So we are planning to use PV rooftop as a sensor, additional sensors.
Okay.
Okay. Well,
no more question from the. Oh no, there's a question.
Verma.
Ankit Verma.
Okay, so how do you check accuracy of building footprint when used for extracting the radiation data in Jupyter Notebook? And I finished the question. The OSM building footprint have offset depending on the data used to generate or person who generated it.
Yeah, you're right. And we are completely completely dependent to the quality of the building footprints for the solar cadastre. But in this pilot, we release this this problem because you are selecting the polygon you want. It's not mandatory to check just a building. You can also, we have in mind some applications, for example, for parking shade. So there is no already existing building, so you can select a part of a parking park lots, a lot of car park, sorry. You can also use this application to select a road and streets. And then with this street, you can have an assessment of the incoming radiation in the streets to provide with new application, I don't know, with electric tricycle with PV on the top. I know that the German aerospace had a project a few years ago about PV tricycles, and having this information, you can optimize. We can imagine things about optimization of the pass routes depending on the slope of the road and the amount of energy you can get at the road. So you can. The idea is to provide you with the free tool of selection, limited to 1,000 square meter, just to select the zone you want. So you are not, in that case, you are not dependent to the quality of the building footprints. You have to select it.
And then again, the limitation that has been, let's say, made for this pilot is this just because we are currently, let's say, only opening these resources to the WEkEO cloud. But again, if you have any application that may need some really large surface, please let us know, answer the questionnaire, and then we can discuss, and we can nail down the proper amount of resources that are needed for your application. This is something, an information of very, very much value in order for us to assess a potential sustainability, let's say, work about how if people want to assess larger zone, what will be the amount of information and support that we need to put in behind. So it is only limited currently just for the purpose of allowing 40 account now on the what we have reserved as an IT support to WEkEO for the period to come.
Yes, and we have this dream to have a fully elastic cloud processing. And if you want to have a big zone, and then we can rent the cloud processing requested, needed for this type of computation, just for the amount of minutes of computation, and release the machine for that. So it's a very nice way of thinking the cloud processing to have on demand. So for the moment, it is limited, but
in the questionnaire, you can write your letter to Santa Claus.
Yes.
And then we will accommodate.
We have one We have 1 year, nearly 1 year.
More than 1 year.
No, for next Santa
Ah,
Claus.
for Santa Claus, yeah.
Yes.
Oh, I was thinking on the longer time.
Oh, no,
so maybe 2 or 3 Santa
Okay.
Claus fiesta. Okay.
And just for the information of everyone, for the solar cadastre we did for ISWT, we didn't use OpenStreetMap data. We used the French IGN and the
Yes.
Revenue Service. You know, these guys who tax your buildings, they want to have a very
and the swimming pool.
precise, and the swimming pool, they want to have a very precise delimitation of your building location and surface. So it's relatively correct. Maybe a bit larger than the building because so they can tax you a bit more. But we noticed that from time to time.
Exactly. So that it's true that it can be used for the solar cadastre for which you need the roof detection. Having a problem in the building footprints leads to problem in the solar cadastre at the end. And in many.
Yes.
So
They
it's very sensitive to the quality of the building footprints.
Exactly. Okay. Time. Still 14 minutes if you want to have another question.
I think they are full of information.
Yes.
So we will. So Lionel, you will send an email with all the information for the conference.
Yes. So well, thank you again, all of you, for attending this session.
Yeah.
So you will receive, all of you, basically all the 40, let's say, people who have booked this session, the instruction to connect. Don't be shy, connect, even if you just have a look, make yourself comfortable, browse the code, and if you're a bit more adventurous, test it and customize it and provide feedback, and then we will reconvene. Again, if you have not yet registered, it is still open for register to the debrief session on Thursday. We will be really keen to hear from you. We thank you very much for participating to this session. And well, let's see us back on Thursday. And thanks for Mathilde and all the SoDa team to support this live
Lionel,
session.
you have just a last remark on the
Okay.
discussion tool from Michael.
Michael, I want to mention the price issue. Perhaps you can take a look at Aurora Solar and Heliosat. They already make people pay for the service in the US. Okay. Thank you, Michael. We will have a look.
Thank you for this information. Yes.
Yes. It's a very precious information.
Thank you very much. Okay, so see you on Thursday, hopefully, and stay safe.
Okay.
Yes.
Bye-bye.
Bye-bye.
Fun with the Python plots.
Yes. Please, panelists, stay on the meeting a few minutes after.
Okay.
Thank you.
Mathieu. Okay.
Have a nice day, have a nice evening, and see you on Thursday. Bye.